So what we're going to talk about today, guys, is standing waves. All right, now standing waves it's kind of a misnomer. It's not really a good name for what we actually see. Okay, the waves do not stand still. They're like the bubbles in the water you're staring at. Look at me. Okay, so they don't stand still, but they form a pattern that appears to stand still. All right, and that's where the name standing waves comes from. We can get standing waves with transverse waves, and we can get standing waves with longitudinal waves. In fact, most musical instruments, at least acoustic instruments, okay, rely on the formation of standing waves, because standing waves are the result of interference. There are going to be patterns of interference that produce a standing wave pattern. Right? What are the two kinds of interference again? Constructive and destructive. All right, so if I have constructive interference and I can, kind of manage the shape of my waves, I can make my sound louder. Okay, I can also make it quieter in certain situations. But for the most part, if I'm playing an acoustic instrument, I'm not looking for destructive interference. That's not something that's going to be helpful to me. All right, so I'm going to be looking at making constructive interference, okay, and causing a wave pattern, okay, that can produce that for me. So that's what we're going to be looking at today. So standing waves result from repeating patterns of interference. All right. Now, if I'm going to get repeating patterns of interference, what properties of the waves need to be the same? Wavelength, frequency, and speed. They all have to be the same. If I'm going to get the waves to always interfere constructively in one place and destructively in another, always in the same place, then all the waves have to be identical. If they're not, then I'll just get a jumbled mess, okay, and I won't get a pattern. So all the waves have to be identical. And for the most part, they're going to be, because they're all traveling in the same what? Right, in the same medium. So the wavelength and speed aren't going to change. Okay, because that's kind of determined by the medium, and the frequency is determined by the source. It can't change. So we kind of fix the waves and make it so that that will occur. Now, if they travel into a different medium, then there could be problems. Okay, but remember, the frequency won't change, just the wavelength and speed will. All right, so we're going to look at how those patterns get formed, and we're going to look at the proper names of destructive and constructive interference areas within the pattern. All right, so the first thing we're going to do here is show you what standing waves look like. You change the length of it, right? You're always only getting a half a wavelength on the string. What you're doing is changing the wavelength. Okay? When you change the wavelength, you change the frequency it can vibrate at. You're not, and I said you change the frequency. I'm not changing the frequency of waves already produced. I'm producing new waves with a different frequency when I do that. Well, destructive interference results in a decreased amplitude. Constructive interference results in an increased amplitude. Okay, so what we were looking at were essentially these three shapes. Okay, this was our first wave pattern. It's the first wave pattern that can be supported by that medium, and as a result, we call it the fundamental frequency. Okay. Everything else, okay, is a harmonic of that. Okay, the fundamental frequency is often called the first harmonic. Okay, the next frequency that produces a standing wave is twice that frequency. So it's the second harmonic. And the next one is the third harmonic. It's 3 times the frequency, and so on and so on. If you had a machine that could produce waves that were the right frequency, you could go to the 10th harmonic if you wanted to. Right? Now, what we were talking about here, and an important skill we have to have, is to be able to look at these waveforms and say, how many wavelengths are there on this string or spring or whatever it happens to be? Okay? In this case, there were how many wavelengths? A half. Here, 1.5, right? So we do have to be able to identify that, especially if we get a problem, right, that says you have a spring that is 4 meters long, and it is oscillating at its third harmonic frequency. Okay? If I know that, then I know there's 1.5 wavelengths on that 4 meter long spring. Can I calculate the wavelength? Okay, so that's what we have to be able to do, right? We have to be able to look at this waveform, okay, and know, all right, even though this distance is 4 meters, there's only 1.5 wavelengths there. Now I can calculate the wavelength. Most of the time, no. Most of the time it's the harmonic, because most of our math has to do with the fundamental frequency. All right, so standing wave is an effect that occurs when 2 or more waves travel through the same place at the same time. Now you could see, as long as those waves were all the same frequency, okay, and all the same wavelength, all the same speed, those areas of constructive interference and destructive interference occurred always at the same spot. All right, now I want you to think back. I showed you a video one of the early days of this unit, and it showed a bridge. Okay, you guys remember the bridge doing this? Okay, that's because that bridge had standing waves traveling along it. Okay, the wind blew on the side of it and started it to oscillate. Okay, and it oscillated, and as the wind increased, okay, the oscillations increased. Okay, because they were all traveling in the same bridge, they all had the same wavelength. They all had the same speed, and because the wind speed was constant, the frequency remained the same as well, because it was the source of the waves. So eventually, a standing wave pattern formed that started to have constructive and destructive interference at various points along the bridge. Obviously, you could see where the constructive interference points were. It was where the bridge was flailing wildly, okay, and where it eventually broke. Right? There were also areas of destructive interference where the bridge hardly moved at all. Okay? This is an engineering problem, to say the least. Okay? Now, I'm going to show you the video here of the whole disaster and kind of what caused it. It actually took them years to figure out why this happened. Okay, I mean, they knew the wind caused it, but they couldn't figure out why the bridge, which was very well designed, okay, and had taken aeroelasticity, which is the nature of something's reaction to wind, okay, into effect. They took it into account. They designed the bridge to withstand it. What they couldn't anticipate was just something that occurred that no one ever foresaw. Okay, and then we learn lessons. Right? So we're going to have a look at that, and then we'll talk more about how we can prevent that. Okay, on kind of future things. So we can see, okay, that in that case we get these standing waves that are forming, okay, and they're really creating these big patterns of constructive and destructive interference that eventually lead to the collapse of the bridge. Well, again, they had mentioned several times that this was a bridge that was that had a ratio of length to width that was longer than anything in history, right? It was a very narrow bridge. It was only 2 lanes, right? Most bridges that would be that long would be a lot wider, but because it had such a long span, they only had, so much material. They wanted the cables to basically do all of the work because it was a suspension bridge, not like an arch or a truss bridge or anything like that. The problem with suspension bridges is that they hang. Okay? If you have a truss bridge or an arch bridge, they're supported from beneath. Right? The weight works down on them, and that's how they're supported. But you can't make an arch bridge that long. Anything that has a span that length has to be built as a suspension bridge, right? And by their nature, suspension bridges are going to be subject to wind. What people didn't realize, and they probably just hadn't done the meteorological studies, was that the wind going through the Tacoma Narrows was very regular. Okay, and because of the nature of the canyon, it always blew straight up the canyon. And just no one had thought of that. It wasn't something they considered to be a problem for the bridge. Okay? Then we get this extremely windy couple of days where the wind was kind of higher than what it would normally be. And that's what led to this incredible oscillation. They had designed into the bridge that it would oscillate. They just never anticipated that they'd get a wind like that sustained for so long. Okay? Had the wind gone down, the oscillation would have gone away. The problem was the wind was sustained for so long that it eventually led to just too much amplitude in the movement. All right. Okay, that's what we're getting to here next. Okay, so if we want to keep this from happening, what we need to do is make sure that the waves that form in the bridge can't have all the same properties. Okay, so the issue they had with this bridge was the tension in the cables on both sides was identical. which meant that the properties of the medium were the same on both sides of the bridge. So the waves could travel at the same speed. What you do now is you make the tension on one side of the bridge greater or lesser than the other. Now, the properties in the cables on both sides are different, so waves can't travel at the same speed down both sides of the bridge. You can never get a pattern of standing waves and constructive and destructive interference to form because the waves won't have the same wavelength or the same speed. So you prevent that from happening. You do the same thing in a building in an earthquake-prone area. The big support pillars are actually built on, they're kind of like shock absorbers, for lack of a better term. Okay, so like it's essentially large elastic or spring-like objects, but all four corners have a different tension or a different spring constant, so that any waves that travel up the building can't amplify each other in terms of sway. Okay, so the building will sway slightly, but it'll never get a wave pattern in it that'll result in it doing this and falling over. Okay, so those are kind of the design modifications that we make now. We just change the tension, okay, on all corners or all sides, and that prevents the standing waves from occurring. Because we said, in order for standing waves to occur, speed, wavelength, and frequency all have to stay the same, be constant all the time. This prevents that from happening. Okay, so like we said here, okay, we've got our standing wave pattern, okay, and then we've got terminology here. Areas of constructive interference are called antinodes. Areas of destructive interference, here and here, are called nodes. Okay, so a node is an area of complete destructive interference. No, a node is always a place where something stops. Yeah, that's what the term means. Node means like nothing or place of stopping. Okay? So an antinode is an exact opposite of that, right? So it's an area of constructive interference. Okay? In some places in Europe, a train station is called a node. The transportation node, it's where everything stops, right? Okay, so we just need to know that term and as well this term. Antinodes are places where maximum vibration occurs because of constructive interference. Okay. So like we were saying here, okay, we use fundamental is the first wave pattern. That's always going to be a half a wavelength for a string, okay? And then, sorry, we don't use these terms here, the overtones. We use the harmonics, okay? First harmonic, second harmonic, third harmonic, fourth harmonic. The reason we use the harmonics is the number matches the number of what? Yeah, well, not waves, but antinodes, right? The fundamental frequency is the first harmonic, one antinode. Second harmonic, two antinodes. Third harmonic, three antinodes. Okay, so it always matches up with that. You're not going to use overtones, so you can cross them off. Okay? We just don't use that term. Okay, making sense so far? All right, so that's what it looks like with transverse waves. Okay, so yeah, like we said here, we're not going to use those overtones, just the harmonics. Okay. The big thing to remember here is that all of those harmonics are a multiple of the fundamental. So if the fundamental is 10 hertz, then the second harmonic is 20 hertz, and the third harmonic is 30 hertz, and so on and so on. Okay, they're always an integer multiple of the original or fundamental frequency. Okay, really important to remember that. Okay. Now, that's how we can create different musical octaves. Okay, so if you're in band or you play music, you know there's like how many C's on a piano? Is it 3? Okay, they're each the same distance apart. So when you play a scale from one note, like from one A to the next or one C to the next, you're essentially going up one harmonic. That's one octave. Okay, same note, but it's the next note on that string, okay, or whatever. Even with a piano, okay, it's a different string, but the string is going to be, you know, like half as long, okay, as the previous note was. Okay? That's why you see that kind of curved shape. If you ever look inside a grand piano, okay, they have that curved shape. Okay, that's because the strings are getting longer as you go along. Okay, questions on that part there? Okay, so again, this is for string instruments. Wind instruments work a little bit differently. Okay, a string instrument takes a transverse wave, okay, and vibrates the air, so causes a longitudinal wave because of its vibration. In a wind instrument, it's either a reed or your lips that are causing the vibration. So your lips or a reed are essentially just vibrating, and they're causing the longitudinal waves to form after that. There are no transverse waves in a wind instrument. Okay, we'll represent them like they are just because it's easier to visualize them, but they are longitudinal waves. Okay, so standing wave patterns arise because identical waves travel along the string in opposite directions. The big thing to remember here is that when I make one wave, it hits this end and reflects back in what way? Inverted, right? So it's always producing its exact opposite at either end. That's why there's a node always at both ends on a standing wave. Okay, because that's where the destructive interference is always going to occur. Okay, and so that's what I just talked about there. If we approach a fixed end, okay, we get a reflected, an inverted reflection coming back to us. Okay. Now, that keeps happening over and over again. I mean, yes, eventually a wave will lose its energy, but what am I always doing if I keep shaking the string? Yeah, I'm always adding more waves. So as waves fade out, more waves are added in, okay? And that's why I kind of got to a constant point there where everything kind of balanced out. At first, you could see that it was increasing in amplitude, and then it just kind of stopped, even though I wasn't really changing what I was doing. Yes, so if it came in as a crest, it goes out as a trough, and vice versa. Yep. All right, so with our string instrument here, okay, we change the length of standing waves formed by an instrument. We change the pitch of the sound. All right, we change the frequency. Again, we're not changing the frequency of waves we already made. We're producing new waves with a different frequency. So if I'm playing the guitar and I'm just using the whole length of the string, I'm not, pressing it down against bridge. Yeah, that's what it's called. Okay. If I'm not pressing it against the bridge, okay, then I'm just using the whole length of the string. I'm going to get the fundamental frequency for that spring, or for that string, sorry. Okay, and its wavelength will be the entire length of the string times 2, right? Because this is only how much of a wave? Half. Okay, so in this case, the wavelength of this wave is going to be 120 centimeters or 1.2 meters, and that's going to produce a frequency of 165 hertz. Yes, that's why the sound changes. Okay, I change the tension in the string, I change the speed at which the waves can travel. So it produces new waves that are traveling faster with a different wavelength and a different frequency. No, the wavelength and the frequency do they do change as a result of. Well, actually, sorry, the wavelength doesn't change, but the speed does. That's why the frequency of the new waves is different, right? If I pluck the string and then I crank on one of those tensioners, right, I hear the frequency change because I'm changing the properties of the medium, making waves with a different speed and thus a different frequency. All right. If I pinch the string against the bridge down here so that I make the waves have a half the wavelength, then what happens to the frequency? It doubles, right? Because the speed remains the same, still the same string. Okay, all I've done is change the wavelength. Okay, obviously with a shorter wavelength, the string can vibrate more quickly and produce a different frequency of sound. Right? So what you're doing, okay, when you pinch the string against the bridge, is you're establishing a fixed end. Okay, past this point, the string can't vibrate. So the string can only vibrate between the, what's this called? Where the, no, where the string's attached down here. Anyone know? Okay, whatever. Where the string's attached down here, I'm sure there's a name for it. Okay, and my finger, that's the only place where the string can vibrate. So I control the wavelength of the sound. I control the speed of the sound by tuning it, and then whatever the string does is what produces the frequency. Okay, everybody all right with that? Now, this is on an electric guitar. On an acoustic guitar, okay, when that string is vibrating, okay, there's that hole right there. Okay, there's air inside of the resonance cavity of the guitar. That air, okay, begins to vibrate because the string above it is vibrating. So those longitudinal waves travel inside the guitar, they bounce around inside the guitar and form a resonance pattern inside the guitar. Okay? That's what produces the louder, amplified sound. If you cover up that hole and then pluck one of the strings, the sound produced is way quieter. Same frequency, but way quieter because it hasn't been allowed to achieve a standing wave pattern inside the body of the guitar. Okay. Now, wind instruments work with vibrating columns of air. All right, so like we said, with any type of horn, okay, or a flute or anything like that, okay, you're making the column of air inside the instrument vibrate. You create different wavelengths or different frequencies of sound by changing the length of the column of air that's vibrating. Okay? You do that by opening up holes. Okay, so you press in the keys or you cover up certain holes with your fingers if it's a flute. Okay, and by doing that, you change the length of the column of air. You're blocking the air from going out certain ones, but allowing it out of others. Okay, and that changes the length of the air column that's allowed to vibrate. Okay? Most wind instruments, are open air columns. That's open at both ends. Okay? The simplest ones are closed air columns. They're closed at one end and open at the other. So if you were blowing across the top of a bottle, that's a closed air column. It's a pretty simple instrument. Okay? If you've ever had a wine glass that's made of crystal and you run your finger around the edge of it, you can get it to do what? Yeah, it hums. Okay? You may not have noticed this, but if you change the amount of fluid inside, changes the frequency of the sound produced. Okay, when it's very full, it produces an extremely high frequency sound. Okay, if it's nearly empty, then it produces a much lower frequency because the column of air that's allowed to vibrate changes in length. Okay, so you change the wavelength, you change the frequency it can produce. Okay, those are open air columns. Okay, so if you're those guys that make moonshine down in the States, and they have a hoedown, they blow across the top of the moonshine jugs. Okay. What's that? Yeah, and they do that. Yeah. All right, so we're going to look at the two types of air columns here. Curtis, yes. Okay, we're going to look at open air columns and closed air columns. Now again, we're talking about longitudinal waves inside, okay, but we're going to represent them as transverse so that they're easier to visualize that way. Okay, so what I'm going to do here is demo this with this resonance tube that I have. All right, so those are the numbers that we've got, okay? We figured out that, okay, we got an antinode at 24.5 centimeters or 0.245 meters. We also got another one at 3/4 of a wavelength that was at 0.741 meters, okay? So I'm going to take this number, multiply it by what to get the wavelength? 4. Okay, so wavelength number 1 should be 98, right? It should be 98, right? Yeah. Okay, so 0.98 meters, all right? Now for this one, okay, this one represents 3/4 of a wavelength. So what I'm going to say is lambda equals 3/4 of a wavelength, sorry. 3/4 of lambda equals 0.741. So if I want to get lambda, what do I do with the 3/4? Divide. Okay, so I'm going to go 0.741 divided by 0.75. Turn on. Pretty close to the same number, right? I had 0.98, now I'm getting 0.988. Okay, so that's pretty close. So lambda 2, 0.988. So we'll just add those together and divide by 2 and use the average. Okay, we've got two trials that way. 0.984, yeah. Okay, so we're going to say our wavelength is 0.984 meters. All right, so wavelength's 0.984. The frequency I used is 349.2 hertz. All right, so if I want to find V equals F times lambda. So I take my frequency and multiply it by my wavelength. So 0.984, okay, times 349.2. All right, that's telling me that the speed of sound in this room is 343 meters per second, which is about what it should be if we use this. First, we have to figure out what temperature it is in here. We have a thermometer. It tells us the temperature. And we're looking at 23 degrees. Okay, so 332 plus 0.6 times 23. Pretty close. Okay, pretty close. I mean, there's other extenuating factors like that thermometer is crap. Okay, and it's not very good. But also that we got differences in atmospheric pressure, and we're not at sea level, all that kind of stuff. That all plays a part. Okay, air density plays a part. So, but still pretty close for just using that rough equipment. Okay, getting a measurement there that's pretty much spot on. All right, so that's a closed air column. Okay, so closed air columns, okay, standing waves are formed that always have a node at one end. Okay, the bottom acts like a fixed end. That's where the stuff reflects off of. That was the water in the tube that we used. Okay, if we were talking about like a moonshine jug or a glass of wine or something like that, where you're blowing across the top or rubbing your finger across the top of the wine glass, okay, then the water or whatever is inside of it, okay, is acting as your reflecting material, and only the column of air is vibrating. That's why we can get different notes depending on how much fluid is in there. Okay? So we get standing wave patterns that always have a node at one end, okay, and we get resonant points every half a wavelength, starting with, which is how many wavelengths? It's 1/4, right? This is 1/4 of a wavelength, okay? And I get a resonant point every half a wavelength after that, right? Because this one started at 1/4, this one's at 3/4, 5/4, 7/4. They're all a half wavelength apart, okay? We get an antinode every half a wavelength. That's just how far apart they are. Okay. The issue with closed air columns is that they don't produce as wide a range of frequencies as open air columns, because every other spot produces a what? Okay. This would be lambda over 2. What would the waveform look like here? Right. There's half a wavelength in the tube, but what's at the top? A node, which means I don't hear anything, right? Okay, I only get, okay, even though this is a resonant frequency, like this is F1, this is the harmonic, or the fundamental frequency for this tube. This is F2. Problem is F2 doesn't make any sound. Okay, this would be F3. This would be, okay, F4. At F4, I'd have this in there. Right? I'd have one full wavelength in the tube, but I got a node at the top, so I don't hear anything. Okay? I only hear sounds where an antinode is produced, and that is at odd numbered harmonics. Okay? F3, F5, F7, okay? F1, okay? At all the odd numbered harmonics, I get a sound. With an open air column, I get a sound at every one of them. F1, F2, F3, F4, all of them. So I get a much wider range of sound from an open air column, which is why most musical instruments are open air columns. Yes, but the nodes are harder to determine, to discern, because I still have the tuning fork. Right? I can still hear the tuning fork, I just don't hear the resonance. It's easier for me to hear when the sound gets louder as opposed to when the sound goes away completely, because it doesn't for me go away completely because the tuning fork's still doing its thing. Right? So yes, I could do that, but it's easier and it's the same with the antinodes. They're the same distance apart as well, and that's why we do it that way. All right, so what we know here, guys, is that when the air column is vibrating at its fundamental frequency, there is 1/4 of a wavelength in the tube. That's where we get this formula from. For closed air columns, lambda equals 4 times the length of the tube at F1. Okay, that formula is on your formula sheet. When we do air column questions, they'll talk about the fundamental frequency, and they'll ask you for things like, what's the speed of sound here? Or here's the speed of sound, what's the length of the tube? Okay, and you'll have to figure those things out using the universal wave equation and your knowledge of the wave patterns that form inside closed air columns. It's On the final exam one, not on that one. Yeah, if you have the one that's not the one I gave you, right? Yeah, if you have the one that's not the one I gave you, it's on there. If you have the one I still gave you that has your name on it, add it. It's not on there because I messed up. Okay, so closed air columns, lambda equals 4L. Okay, at F1 because it's 1/4 of a wavelength in the tube. Okay, everyone follow how we're getting that formula, right? That's lambda over 4 is the length of the tube. Okay, so 4 times the length of the tube is lambda. Okay, questions on closed air columns? Okay, then I think what we will do is we'll leave it at that for today. I'll talk about open air columns tomorrow. Right? Next week, Monday and Tuesday, we'll be doing lab activities. They will not be handed in for marks. Okay, they'll just be ones we do in class. We'll talk about the analysis and all that, but we're to the point where you guys need to be looking at studying for your unit exams, final exams. I'm not going to load you up with more assignments at this point. Okay, you're welcome, but okay, you still need to do them and pay attention because there'll be stuff on the unit exam about the lab activities. Okay, we'll still do them on Google Classroom and all that. You're just not going to turn them in. Okay, we'll do them in class. They won't be for homework. All right.